Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there. So let us discuss this following derivative, so we can understand how to basically take part in this kind of derivative problems and how to understand if they're actually going to help us in doing the probabilities and stuff. So let us see. Okay, so well, the integration is from 0 to pi, and what we want to integrate here is something called log of sine x dx. So our integral I is integral from 0 to pi log of sine x dx, and we want to integrate it, and we want to see if this function makes sense. So okay, actually we want to integrate from 0 to pi by 2 because that is a better version of it, because from 0 to pi what you need to do is you need to understand that that can also be translated into 0 to pi by 2. That is a property we haven't learned yet, but we will learn it soon. So anyways, if we were to evaluate this integral, we recall that the property a to b f x dx equals to integration from a to b f of a plus b minus x dx. If you remember that from the basic integration course, of course that video would be added at the end of this video, just to clarify things, because we, as I've told in other videos as well, we like to include the videos that are supporting the current problem within the video so that you can learn it inside a single video itself, and you don't need to switch to other videos, because yes, if you want to learn it alone there are other separate videos for the same video, but if you want to learn it together it's better to learn it from a single video and not switch videos that merely distracts you. So recall that a to b f of a plus b minus x dx is equals to a to b f of x dx. So this means that whenever you have a limit with a to b and you have a function f of x, what you can do is you can use it as f of a plus b minus x dx, right? So this property is pretty useful, but then again this property needs to be a bit more reversed for us to use it. Now how do we use it here? Because we see the limit here is basically about 0.02 pi by 2, and our a is 0 and our b is 2, right? So what we can do is we can use this property to understand that 0 plus pi by 2 minus x would be pi by 2 minus x. So basically our integral would be something like this: 0 to pi by 2 log of sine of pi by 2 minus x dx. And what this does is it transforms this integral into something like this, because sine of pi by 2 minus x is log of cos x. What we have is 0 to pi by 2 log of cos x dx. And when you add, since this is also I, as we have already told, because the integral is named as I plus I is 2i, and 2i would be equal to log of sin x plus log of cos x, and you know the logarithms add together to give a multiplication. So basically what it would be is 0 to pi by 2 log of sine 2x by 2, because you know 2 sin x cos x is basically sine 2x, right? Sine 2x by 2 dx. And using some manipulations we can write it as log of sine 2x minus log 2. Minus log 2 part would be minus pi by 2 log 2 with the base of e, and this part would be, when you substitute for 2x, but you get the limit as 0 to pi, and what you get is sine of x, and this x would be like half into 2x, so what you get is 1 by 2. So after substituting for 2x, I'm writing it directly 0 to pi, and this would be log of sine x dx. And it can be proved that the integral from pi by 2 to pi by 2 to pi can also be written as log of cos x. So this integral is basically 2 times I, and what we get is I equals to minus pi by 2 log 2. Now the required supplementary materials will also be provided with it after the video, so you can watch it there. We would start off with something we know as the binomial formula. So binomial expansion. Now what is a binomial expansion? So a plus b whole to the power n, this can be expanded when n is a natural number as follows. Like this. So using this we can also find out this expression right here, that 1 plus 1 by x whole to the power x expression, where we know that x is a real number, but for the time being we can actually find out something about it. Like this is also valid for rational numbers and real numbers, but just that we have not done that yet, but we can still use this to find like this, but it would be an infinite series because of the x here. It should be x ck into 1 is irrelevant, so 1 by x whole to the power k, right? Now the thing that is to be noted is this term here. If you just write it as a function of both k and x, it can be written as x ck into 1 by x to the power k, right? Now how to define this binomial coefficient in terms of rational numbers or real numbers or even negative numbers? So there is a definition. It is same as the one that you define with natural numbers, but just that you do not do the factorial thing here, because factorial makes no sense, right? Because you cannot really find out 0.5 factorial because it doesn't go back to 1. Factorial means that you multiply the integers consecutively until you get 1. But in case of real numbers, in case of rational numbers, that's not how it makes sense. Okay, so what makes sense is this: xck can be written as x into x minus 1 into x minus 2 and all the way up to x minus k plus 1 divided by k factorial. This is the expression, and you have a x to the power k extra in the denominator, which gives us the expression for this. And we are literally trying to find the limit of this expression right here, right? So one of the x's can be cut off, obviously, and what we do get is this: x by x into x minus 1 by x into x minus 2 by x and all the way up to x minus k plus 1 by x, and then there is a 1 by k factorial. And now there are k terms, so I have divided all the k x's in as denominator to this one. So this gives us 1 minus 0 by x into 1 minus 1 by x and all the way up to 1 minus k minus 1 by x whole divided by k factorial, right? Which can be written in the product form as follows: summation r equals to 0 to k minus 1, 1 minus r by x, and there is a 1 by k factorial outside, right? Now this definition gives us the notation for factorials, and it can be proved in later sections when we will be discussing about infinite series and infinite products, that this product right here is equal to 1 by k factorial when you put the limit, of course. So when you put the limit, this product is equal to 1 by k factorial into ek factorial, which gives you answer as e. But this product can be evaluated in multiple ways actually, because this product right here has an integral form as well as a differential form, and using the methods of Riemann integration, a lot of times infinite limits can be evaluated, which we shall learn when we get to the integration section, or maybe we can have a glimpse of what's happening, but for now this should work. So this is the basic proof. Now let us do some examples. Example 1, find the limit of sin x by x as x goes to infinity. So basically what we are asking to find is, we can denote the limit by L. So denote the limit by L, and L would be equal to limit x tends to infinity sine of x by x. Okay, now how do we do this? Now this cannot be done because obviously you remember a quite close one where x tends to 0 was given, and if x was going to 0 we knew that sin x by x approaches 1. But here the case is a bit different, and we can clearly see the denominator x, as x goes on to become larger and larger, the denominator becomes much larger, right? And the number should be decreasing by then, the limit value should decrease a lot. But doesn't sin x also increase? No, it doesn't, because we know that sin x for every real value of x lies in the closed interval -1 to 1 for all x belongs to real, right? So this is a property of sin x, that sin x is bounded. Then we can see that sin x is greater than equal to -1, then sin x by x should be greater than equal to -1 by x. Similarly, sin x is less than equals to 1, then sin x by x should be less than equals to 1 by x, right? It is evident that limit x tends to infinity 1 by x is equals to limit x tends to infinity -1 by x is equals to 0. So both the limits actually go to 0 irrespective of the sign, and also since we can bound the function sin x by x using this as we have done here, so we can basically write -1 by x less than equals to sin x by x less than equals to 1 by x, right? Now I'm going to quote a theorem here. It's called the sandwich theorem. It's called the sandwich theorem. It says that if fx, gx, hx are continuous functions then if fx is less than equals to gx is less than equals to hx and limit x tends to a fx equals to limit x tends to a hx, and both of them are equal to some alpha where alpha is a real number, then the sandwich theorem states that then limit of x tends to a g of x must also be alpha. So this is the sandwich theorem. That is, the function g of x has been sandwiched in between the functions fx and hx. Okay, so hx is the upper bound for the function, fx is the lower bound for the function, and it is given that the function fx and the function hx, both of them go to some real number alpha when x tends to the value a. So both sides of the limits in which the function gx is sandwiched goes to the same real number alpha, which means that the function in between must also go to alpha, otherwise the inequality would be violated. There is a whole proof for this, but we are not really going to do the proof right now because of the complications, because we need to know what is an epsilon delta definition of a limit. This is completely an analysis course, so I'm not going to code analysis right now unless we need it when we go to the further chapters in probability. So using this, we can see that since equals to 0, we can say that limit x tends to infinity sin x upon x must also be 0, since minus 1 by x less than equals to sin x by x less than equals to 1 by x. Since sin x by x is basically sandwiched between minus 1 by x and plus 1 by x. So that would actually solve this problem. So as I said, this is not like a regular problem, but problems like this would be very much evident. Okay, for the next problem I would need a footnote here, that is the footnote of a derivative of a function fx. So derivative derivative of x f of x at x equals to a is defined as, I'll give you the formal definition of derivative for here, and we are going to revisit it when we start derivative, but for this problem this much information is sufficient to do the problem. So f dash a is basically equal to limit x tends to a f of x minus f of a by x minus a. So this basically is the definition of derivative. Okay, this limit, the value of this limit gives you the answer to f dash a. Now the problem, given f of a equals to 2, f dash a equals to 1, g of a equals to minus 1, g dash a equals to 2, then find limit x tends to a g of x into f of a minus g of a into f of x divided by x minus a. So consider the problem. We are given that f and g are two functions which are first time at least once differentiable at the point a, and it is given that f of a is 2, g of a is minus 1, while f dash a, which means the derivative of the function at the point a of f is 1, while g dash a is 2, right? So g dash a is 2 doesn't mean that the derivative of g is 2, it rather means that the derivative of g at the point x equals to a equals to 2. So don't be confused with the definitions and the terminologies I'm using, because it's important that you understand them distinctively. Now limit x tends to a, g of x into f of a minus g of a into f of x. What we are going to do here is something like this. We are going to add and subtract GA FA. Minus G of A into f of x, and we are going to draw a line x minus a. Now why did we do that? Because we are going to separate this first two terms and this last two terms and write them as a separate limit. You will see why. Because we want to really find out how to evaluate this kind of problems using all the information given in the problem, and whatever we just learned a bit ago about the definition of a derivative, which you can see here, this would be handy here. So this becomes g of a into f of a divided by x minus a, plus another limit x tends to a, g of a into f of a minus g of a into f of x divided by x minus a, right? Now what we can do is we can take the constant common, which is f of a, from the numerator, and we can write this as f of a into limit x tends to a, g of x minus g of a by x minus a. Similarly, we can take minus ga common here, and we can write limit x tends to a, f of x minus f of a by x minus a. Now if you remember, this was the definition for the derivative of the function at point a, right? So f of a into g dash a minus g of a into f dash a. This would complete the derivative section for this one, and now it's just a matter to put the value. So f a is 2 and g a is minus 1 and g prime a is 2, so first two terms are 2 into 2. So this gives us the value of 5. So this would actually solve this problem, but as I said, you would need this definition. So once you learn the derivative section, I do not think this would be any more required, but these are the basic things that you should know. Okay, let's move on to the next problem. So we are given to find the following limit. Okay, so this is the problem that we need to find. Limit x tends to infinity, and in the numerator we have root over of x square plus a square minus root over of x square plus b square whole divided by root over of x square plus c square minus root over x square plus d square. Now To this kind of problems, we, as I said, we need to first rationalize. So let us begin the process. Let this be L. So this is equal to, so we shall multiply by this x square plus a square minus x square plus b square into root over x square plus a square plus root over x square plus b square. So this was multiplied, and also we need to multiply by the conjugate of the other term, which is x square plus c square plus x square plus d square. You will see why I did that, because we would need that here. So this thing, first we write whatever there is in the question, x square plus c square minus x square plus d square multiplied by x square plus c square plus x square plus d square, and then the extra term of root over x square plus a square plus x square plus b square. Now once we do the formula, because it's a minus b into a plus b, it turns out as follows. It becomes x square plus a square minus x square minus b square into x square plus c square plus x square plus d square over root. Similarly, in the denominator, it becomes x square plus c square minus x square minus d square into root over of x square plus a square plus root over of x square plus d square. Okay, now the x squares get cancelled off in these two expressions, and what we get is this: limit x tends to infinity, a square minus b square by c square minus d square, and now multiplied by root over x square plus a square plus square root of x square plus d square, actually it would be c square, divided by root over of x square plus a square plus root over of x square plus b square. Right? Now we divide up and down by x to get something. So firstly we can take the constant out, and then we can divide up and down by x to get the following: root over x square plus c square plus root over x square plus d square whole by x divided by root over x square plus a square plus root over x square plus b square whole by x. Now this x can be absorbed inside the square root of each term as root over of x square. So once you put the x inside the square root, it becomes by x square, right? So the limit becomes a square minus b square by c square minus d square, limit x tends to infinity. Numerator becomes root over of 1 plus c square by x square plus root over 1 plus d square by x square divided by root over 1 plus a square by x square plus root over 1 plus b square by x square. Now since we know that this individual term c square by x square, d square by x square, a square by x square and b square by x square go to 0 as x tends to infinity, the answer simply becomes a square minus b square by c square minus d square into root 1 plus root 1 by root 1 plus root 1. This is essentially 1, so the answer is a square minus b square by c square minus d squared. So this becomes the answer. So as you see, some of these problems are a bit challenging than before, because you might have to do a lot of calculations and you have to be very careful, and then again you need to know the method to do all of them. But if you have learned the third chapter completely, if you know how to rationalize and you do not actually make like imminent errors, I do not think you would be getting this wrong. You might be getting this right every time you attempt it. But the only two problems that were very different with this: first, we used the sandwich theorem to evaluate a limit for the first time. So this is a technique which you are not going to forget now. So you can try it whenever you are stuck at a problem. You can try to bound that function and see if both the bounds yield you the same result at the limiting value of the required function. Then the function itself would be that value. And then again, we learned about the derivative of a function and at a certain point and the definition of it. It is called the derivative from first principle when we evaluate it by the limiting definition, and using that we have solved a pretty good problem, I would say. So these three problems laid a lot of foundation to a lot of things, and in the next chapters we would also try to continue this and slowly introduce the concept of derivative and do problems on derivative directly. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sin b cos a. So this is the formula, right? So using this formula, we can see that sin of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sin a cos h plus sin h cos a minus sine A divided by h, right? So what we can do is limit h tends to 0, sine h by h into cos A. So we can just take the second term here, and we can take the first term common, and we can write limit h tends to 0, 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of A, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one, sin A into, now we first use the formula for 1 minus cos theta is equals to 2 sin square 2 by theta. So using that formula, it becomes minus 2 sin square h by 2 by h, and this limit goes to 0, because firstly sin h by, if it was sin h by 2, we could have found the answer, but since it is sin square h by 2, it goes to 0. So the answer is cos of A. So the derivative of sin of x at the point A is cos of A, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows. F dash A would be equals to limit x tends to A, f of x minus f of A by x minus A, from which we can substitute h equals to x minus A to find the new definition which was more useful to us, which is like f of A plus h minus f of A divided by h, right? Now this would give us limit h tends to 0 cosine of A plus h minus cosine of A whole divided by h, right? So this means now we have to use the formula. Now trigonometry that cos of A plus h is equals to cos A cos h minus sin A sin h. Using this formula, what we can do is as follows. Using this, we have f dash A equals to limit h tends to 0 cos of A cos of h minus sin of A sin of h minus cos of A divided by h. So we can again distribute it as follows. Take cos of A common, and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of A common, limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of A into 1, because this limit is 1 as we have done in previous examples. So the answer becomes minus sin of A. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: h tends to 0, f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common, as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1, as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down: list of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. is a to the power x. Number 5. Number 6. of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should do. This should actually work pretty well. So let me write down some more rules. If fx and gx are two differentiable functions, differentiable functions, then ddx of fx plus gx is equals to ddx of fx plus ddx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if we are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart so that you can just tell them at your lips. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.